Okay, guys, we're gonna get started here. So,
I'll write it down.
okay.
Yes. Stop.
No.
Oh, yeah.
And then it brings it.
I was saving opportunity.
No. And then at the very end, you're like, I don't know what to feel.
All right, guys, are there any questions on the first couple of problems, like the first four, numbers 1 through 4? Anything that stumped you?
Wait, what is
So today I'm gonna go over a couple examples from 5, not many. A couple examples from 6 and 7, and then we'll see how time allows. But, this is all review it, but I know that we didn't spend a ton of time on these. We maybe did like 4 last year, so if you forgot, so I understand. These are also like, they're not like that. I mean, it's just something that kind of a classic limit question. They're a little obscure, but they're out there. So, okay. Anyway, so first, look at 5A. You know, we'll do a couple of these. These ones are very easy once you know the trick. So, if you think graphically, the answer might pop out to you right away. You know, it's like the graph. If you graph this, it would look like this. So what's the answer? 3. Okay. Now, not like you have to graph them, but so when you look at this, you go, well, I got a sum of terms. So the way limits work is, and if you want to get technical, you could say something like, oh, the limit of f of x plus g of x is the same as the limit of f of x plus the limit of g of x. Like if you wanted a precise, rigorous mathematical statement, something like that. So, which is a very,
Really?
Yeah. So that's a property of limits, which is, this is a big thing in calculus because if this wasn't true, well, things would be a lot harder. Well, Mr. Thompson here? Yes. You've been summoned, Liam.
You've been summoned.
Hey, September 30th,
What's that?
South Park Pandemic Special.
Oh, I'll have to watch that
Gotta
one.
watch that.
Yeah. Classic. I love that show. He likes it too. So, what this says is the limit of this. So, what's the limit of this term as x gets really big? Well, this term approaches 0. This term just stays the same. He doesn't care what x is. So, 3 plus 0 makes 3. Sound good? So, like, let's compare that to, I don't know, look at the one right below it, where these ones often confuse people. And I think the confusion arises from, I don't know, trying to maybe think about the whole thing at the same time. So you've got, what's the limit of x plus 1 over x as x approaches infinity? It's DNE, yeah. This would approach infinity because what happens as x gets really large? Well, this term is approaching infinity, and this term is approaching 0. So, for example, when x is 1,000,000, you have 1,000,000 plus 1,000,000. So this guy doesn't actually equal anything; it just does not exist. It is valid. You might see this in like a future class. You could possibly see someone write that. It's sort of a loose use of the equal sign, because technically, it just depends on what conventions you're using. You could say that, oh, this limit equals infinity. And everyone knows what that means. Everyone agrees that that means that this thing grows without bound. So just throwing it out there. For this class, you know, if you are taking the AP exam, you will never have a question where the answer is like infinity. That limit would always be does not exist. You can never be wrong to say that that limit doesn't exist. We'll go. B? What do we think? For B, again, you break it, the answer is 3.
Yeah.
So what's the limit as x approaches infinity of 2 plus x over x plus 2? Okay. So what is this term doing? Well, this term just stays the same, it approaches 2. This term, because you have the same degree on top and bottom, is approaching 1, so the answer is 3. All right, so those are all, there's not a ton of them because I just kind of was like, just remember those exist. Those are out there. Those kind of questions. We already covered this type of factorization when we talked about holes. It's the exact same thing with the square roots. So like, for example, you can factor x minus 9 into root x minus 3 times root x plus 3. Look for some cancely-wancely action. So, you guys don't need to cover that, right? Should be pretty fresh, hopefully. If not, talk to me individually once we get going here, and I'll help refresh your memory. Okay, so these ones. So look at that first one and think. Test your math instincts, your algebra instincts. Not good. Well, when you do math, a lot of the time you don't know, if you're doing a challenging problem, you don't really know what the first step is. And you have to kind of, a lot of times, guess and check a bit and say, well, I'm not really sure, but I can try this and see what happens. And a lot of times it's not a fruitful attempt. A lot of times you try something and you go, that didn't help at all. That actually made it more complicated. So in this case, if you had to guess, what do you think would be, what could we maybe do to this to manipulate this? Anyone have an idea?
Square.
Multiply by 3 plus the square root of 9.
Hold on, one answer was square something.
Square.
Put that in the back burner, talk about that in a second. Anyone else? I heard someone else.
Multiply by 3 plus square root of 9.
Oh, yes, that's right.
Yeah, like a conjugate idea. So the problem with squaring the top and bottom is like,
Does it make it harder?
well, no, it's actually not even allowed because like, say you had a number like 4/5. I know 4/5 is already simplified, but let's say you squared the top and squared the bottom. You'd be like, that's not even the same number anymore. So then the problem with that is think about when you square the top and square the bottom, what you're doing is multiplying it by 4/5. So while it's tempting, you go, well, we just multiplied this number by a non-unit. So you actually change its value. What Jesse mentioned is this idea of multiplying by a conjugate. So I'll give you a simpler example, which is like, say you had, 7 over 1 plus root 3. Capital T, they might say, rationalize that denominator. And what you would do is you'd multiply by 1 minus root 3 over 1 minus root 3. And what that does is the top you'd have this, and on bottom, because it's an a plus b times a minus b, remember that famous identity? It's right at the top here. A plus b times a minus b makes a squared minus b squared. That's really well-known identity. So the top and the bottom would be 1 minus 3, right?
Yeah.
Everyone okay with that? So there you go. We've made the denominator rational. So great. So anyway, so I was just trying to show that what Jesse mentioned is just a more complicated version of a simpler principle, which is where you multiply by the conjugate. So the conjugate here is 3 plus the square root. Again, notice we're doing it on top and bottom. So then holistically speaking, you're just multiplying this by 1. So, all right, algebra time. So on top, we've got all right, so there you go. I didn't distribute the 2x over the sum because, I don't know, got a feeling. Well, do you see how, I mean, you have 6x plus 2x times root 9 plus x, which you're like, okay, is that really going to be easier to deal with? And I'm hoping that on bottom, so try to look ahead. Do you see on bottom what might happen once we apply this idea? 9 minus, which means the bottom is just what?
No, sorry.
Negative x.
Negative x. And the negative x can just cancel out that x.
Yeah.
Yeah, so what we've got is, I hope everyone followed that. So the bottom is negative x, right? 2x divided by negative x is just negative 2. Did everyone understand that? That step?
Yeah.
Yes. No questions? Okay. So then, what is the answer to the question?
Negative
Negative 12.
Oh, indeed.
Well, now indeed. By the way, I was a bad man. I didn't actually plug the x. I didn't plug the 0 in to test it at the beginning, but let's do it retrospectively or retroactively, whatever. Plug in the 0, you get 0 on top, and the bottom would be 3 minus root 9, which of course is 0, 0 over 0. Okay, all that stuff we did was fine. So don't forget to check that. So, you guys feel okay about that process?
Yeah.
Just to avoid any maybe confusion here, on part B, what's the conjugate of the top here? So the top is,
It would be square root of 5x plus 4 plus 2.
yeah. So you starting off with this, it's a limit, of course. So the conjugate in this case would be what you, oh, sorry, I wrote it
It's
wrong.
minus
There's a minus 2, isn't there? All right. So there's your limit. Of course, if you plug in 0, you get root 4 minus 2, which is 0 over 0. So what you want to do is, the question was the conjugate. Notice the thing under the radical is identical, 5x plus 4, 5x plus 4, and you're just changing the sign. So if there was a minus, it's a plus. If it was a plus, it's a minus. Doesn't really matter what order it's in. So notice on this one, the radical was first. On the first one, the radical was second. Didn't really change anything. It's the same idea. It's still going to be this a plus b times a minus b. Okie dokie. All right, let's cover one more thing. And then we'll have just some more time for like 30 minutes. Okay?
Yay!
Yay! Absolute values. Absolute values.
Oh, yeah.
Okay. I wrote it backward. Doesn't matter. Okay. There you go. So this function is kind of popular when you're studying limits and continuity. Does anyone think they have maybe a reason Why would this function be so popular?
Because like half it's like it's an x value, right? It's like this. Then it's its absolute value, it can only be on this half of the graph. That made any sense.
It's positive when x is positive and it's negative when x is negative.
That's getting to it. It's one of the simplest graphs you can. Yes, Alyssa, you got an answer?
I'm not.
You maybe can fill in the blank here. It's one of the simplest functions that you can write that has a
Denominator?
jump.
Oh, okay.
I wouldn't say discontinuity because I can write 1 over x. That has a discontinuity, but it's the simplest function that you can write pretty much that has a jump in it. Because usually to make a jump, you need to make a piecewise function. Those are always a little bit funky to work with. You got a comment?
I just know.
Oh, yeah, what does it look like?
When it's less than
Why
zero,
are you using words when you can use interpretive dance still?
when it's less than zero, it's consistently equal to -1, and when it's greater than zero, it's consistently equal to 1. And there's just a jump.
Yeah. So yeah, this question becomes pretty simple if you just think about if you pick any positive number. So first start with easy ones like 3, 7, like whatever, positive numbers. You plug in 3, you get 3 over 3. Plug in 7, you get 7 over 7. But it even works if I plug in really tiny numbers. What if I plug in 0.001? You still get 1. So no matter what number you plug in, as long as it's positive, the y value is 1. And then for negative numbers, this is exactly what Dylan said, which is now if it's negative, the top's negative, bottom's positive. Same argument though. What's the only number that can't go in here? 0. You can't do 0 divided by 0, it's undefined. But you can take the limit. The limit as max values approach 0 from the right would be positive 1. So they like this function because it's just a very simply written function that illustrates a jump. Okay, so on a jump, the right limit can exist. Now it's not the greatest function that's constant on both sides, it's just not, I mean, a more illustrative function might, be all kind of curved on both sides. But anyway, this one shows up a lot because of that problem. Okay. So whenever you're doing a question like this, you just kind of want to think about it in the same way. So there's a whole bunch of different examples here where, oh, by the way, just right limit's 1, left limit's -1, and the limit is undefined, does not exist. So the limit does not exist. Remember, for the limit to exist, the right limit and the left limit would have to be the same. They have to be converging to the same y value. If they're doing this, right, there does not exist. Okay. How about like D though, where it's absolute value of x over the square root of x squared.
Because I literally just did the same idea. Like, this is the same thing here when I do the chain. But I didn't do that.
This one's a little weird because what might be helpful for this one is to realize that the square root of x squared is the absolute value of x. Those are equivalent expressions.
Yeah.
So this basically is the same as saying absolute value of x over absolute value of x, which means it's always equal to 1, except when x is 0. So big difference on this graph, the right limit exists, the left limit exists, and they are equal to each other, so the limit exists. So there you go. All right. Other than that, I mean, any questions on any of this stuff, guys? We good? Okay, let's have some work time just to knock out these limits. I'll be available for questions if you have any questions. Yes.
Ooh.